Today I'll be talking to you about co-design for heterogeneous integration and taking a perspective from failure analysis. This work was performed at Sandia National Laboratories from a large group focused on everything from material synthesis through failure analysis. The Department of Energy Office of Science released their basic research needs for microelectronics report in 2018, and in that report they challenged the scientific community to rethink the approach for innovation for microelectronics. Pulled from the report, advances must be conceived and developed collectively in a spirit of co-design, where each scientific discipline informs and engages others. Successful co-design will result in parallel but intimately networked efforts to create radically new capabilities that will not have resulted from the historical linear development process. At Sandia, we asked the question, could we use artificial intelligence to enhance this co-design? Pulled from the ASCAC subcommittee from 2020, AI won't replace the scientists, but scientists who use AI will replace those who don't. Further, when we look at designing hardware rapidly, how can we develop learning cycles that rely on accurate understanding across multiple length scales, everything from single atoms to millimeter-sized integrated chiplets? And further, how do we take that construct of AI-enhanced co-design for microelectronics from driving discovery and innovation through to reliability? One example that we've worked on is fusing data across multiple modalities for electroplating thin films. And here we're looking at electroless nickel plating versus electroplating. And when you're looking at a pre-process, there's precursor characterization that occurs, a lot of mod sim work, all that work leading into developing the experimental design. Once you're in process, there's a number of different modalities of data that you can collect, from time series data, in situ characterization. And then on the back end, post-process, a lot of destructive failure analysis that occurs, including microscopy and characterization, on through to property, performance, and aging measurements. So how do we fuse those together in order to discover reliable materials as well as processes? Another aspect that we can look at is integrating these multiple data sets from pre-process, in-process, and post-process with governing equations. From a fundamental perspective, we might understand how growth occurs, diffusion occurs, and from there we might be able to develop some reliability models or lifetime expectations. At Sandia, we're trying to optimize our process through a program that we've developed called Himalaya, spelled intentionally that way, where we're taking these different multimodal data sets and incorporating a feedback loop with neural networks and artificial intelligence, machine learning algorithms implied, some of those utilizing conservation laws or PDE constraints that we pull into it, as well as machine learning on images. So we can pull these multiple data sets into predictions on process structure and properties and use those with high throughput testing to estimate what our materials reliability might be. Now this is an example of working through one single process step here, electroplating or electroless nickel thin films, and trying to use high throughput characterization through to end state optimization. Now when we start looking at heterogeneous integration, it's a much more complex system. And you can see this valley of death perhaps starting to grow between not only just this feedback loop of high throughput testing, but in complex systems moving to materials reliability. So that chasm is opening as we start to explore more complex heterogeneous integration and advanced packaging technologies. And so how do we take that single material reliability and lifetime estimation and failure of complex parts where we have mixed materials, interfaces, as well as numerous failure mechanisms? Now, I won't state that we have answers to this. However, it's important to take a look at end state and how that might affect. So we're all probably very familiar with the observer's paradox. How do we use physical limitations to drive design limitations? And how do we observe those without inducing effects? On the left-hand side here, you can see an example of one of our experiments here, looking at advanced packaging techniques with indium bump bonds and a 3D heterogeneous integration, in which our gallium fib focused ion beam induced artifacts into our intermetallic layers here, causing this voiding to occur. Now, this wasn't from the actual design limitations or processes. It was induced from cross-sectional analysis. Through some development, we're able to determine optimal techniques, including using, instead of a gallium ion beam, utilizing a xenon plasma fib at cryo temperatures. On the right-hand side here, just the cooling down, minimizing those artifacts. So from a design perspective, as you look towards the future and more complex hardware, failure analysis techniques need to be developed for those new integration methods in order to reduce any observations of false failure modes. When we look at this co-design network of new structures, not only should we be focused on development and innovation, but also looking for FA and materials characterization as well. And I might say that FA should be at the center of this, as that is a very important feedback loop when it comes to understanding our limitations and design parameters. So end state performance and reliability of next generation HI products relied not only on optimal designs of hardware and software, but investments in FA techniques as well.